Okay, so with all these topics, the story keeps improving. Process understandings get better. Predictive understandings also hopefully improve, and predictions should improve over time, especially as to how global warming begins to affect these intrinsic processes like the active break periods within the monsoon. We've already seen many aspects of this, so just remember we are still trying to explain the decreasing mean rainfall observed over the Indian subcontinent, even though there is some debate about whether the decline from the 1960s has stopped, and then there is a recovery of the monsoons, but not all data sets show this. And then there is the monsoon depressions. We looked at a nice paper by Arindam Chakravarti's group where they argued, I think it was Karmakar and Chakrabarti who argued that the synoptic scale depression, so 3 to 10 days, let's say 3 to 9 days, have increased, whereas the lower frequencies like 10 to 20 days, 20 to 60 days have decreased. So this story is always quite complicated, and this is a new paper from Pankaj Kumar's group from IISER Bhopal, and I just wanted to include it here and start a new section under this series of podcasts called New Findings in ISVs, because I suspect we'll continue to get more and more stories like this. So I'll just briefly show two slides and say what the main results are. Basically, they are again diagnosing observations, reanalysis products to look at how the active break periods have changed over the 2000 to 2019 period compared to 1980 to 1999 period. Obviously very short, but in terms of the global warming, this is quite relevant in terms of the last 4 decades overall, right? And how things have changed in the last 2 decades versus the previous 2 decades. So this shows a change in vertically integrated moisture transport. Blue indicates more moisture transport and red indicates less. So there is more transport here and red a little bit over here. Only significant quantities are shown. And the arrows, of course, indicate the magnitude and direction as well. Vertically integrated moisture flux convergence, flux divergence for the entire atmospheric column. Here, red indicates convergence, so that corresponds to increased transport, for example. So this is for active and this is for break. So keep that in mind. Same here, active and break, so increased convergence, reduced convergence or divergence during the break period. This is comparing the latter 2 decades, 2000 to 2019 minus 1980 to 1999, composites of active and break periods. Okay, so lots of information, but just make sure you follow. And C is the low level relative humidity and transport in vectors during active and break spells at 850 hectopascal. So basically this is showing somewhat an indication of the dynamic and thermodynamic changes, so circulation and water vapor transport, moist dynamics changes. So during the active period in the latter 2 decades, there is enhanced transport into the core monsoon zone where the active and break periods are typically computed, as we have seen before. And during the break period in the latter 2 decades, there is obviously, you expect a cyclonic circulation during the active period, which is anomalously not so obvious here, but you can see that in terms of moisture convergence from enhanced vertically integrated moisture transport here, whereas the break period, that is directed more into the Bay of Bengal and the Indo-Gangetic Plain, Himalayan foothills, northeast show much reduced vertically integrated moisture transport, and similarly here the moisture convergence is greatly reduced over the Western Ghats, and there is also slightly reduced but more focused on the northern part of the Western Ghats here, but the focus really is on the core monsoon zone because that's how you define active and break periods, and this paper particularly focuses on July and August as the main season. So I won't dwell much on the humidity, but it's consistent with the water vapor transport, so there is increased low-level relative humidity and transport here, and by the same token it's reduced over here. But more interestingly, if we look at the series of processes they highlight, this is a graphical representation of the mechanisms governing the PEs, the precipitation events which crop up during the interseasonal variations. Mean precipitation of July and August, that are the peak monsoon months, are declining. So we already talked about the decreasing monsoon over the last several decades, and potentially related to land not heating as much as the ocean because of the pollution, solar dimming, aerosols, and so on, which is related mainly to the decreasing mean precipitation of active spells. So this puts a slightly different twist to it, in the sense that the solar dimming or whatever other process is invoked for the trend, the downward trend in the mean monsoon, is coming from declining mean precipitation during active spells. So this is consistent with the story that everything over India, the Indian subcontinent monsoon, the seasonal cycle, El Nino, La Nina, IOD, Atlantic Nino, Arctic forcing, global warming, everything project onto active and break spells. So if mean monsoon is decreasing, then is it coming from the active or break periods? Here the argument is that the number of events during rain, precipitation events during active periods are increasing, but the total rainfall is decreasing. So the trend in seasonal rainfall is coming from active spells precipitation drop, although the precipitation in break spells has enhanced due to increased intensity of the precipitation event falling in break periods. So break period is still characterized by rainfall being one standard deviation below the long-term climatology, but the intensity of the rainfall events that do happen during break periods have gone up during the latter 2 decades compared to the previous 2 decades, but this is not able to compensate for the declining rainfall in active spells. The increase in precipitation is supported by the factors indicated in blue boxes here, while decrease is related to the factors indicated in yellow boxes. So there are blue and yellow boxes with decreasing feedbacks and increasing feedbacks onto precipitation events. So let's look at these few things here. So there is positive feedbacks happening in the blue regions here. This is enhancement, positive feedback. This is declines, and these are things that lead to a decrease, and this lead to an increase. So keep those in mind. So enhanced convectively available potential energy over the southern central India. This is Cape, just briefly, is basically buoyancy. So if you take temperature of an air parcel and compare it with its surrounding or the environment, then it's buoyant, so it keeps rising till it reaches its equilibrium level. So generally Cape is averaged buoyancy of that sort from the level of free convection to the equilibrium line. Don't worry about it if you don't get the details. It's an indication of driving convection because of this convectively available potential energy. So potential energy is converted into convective kinetic energy. Reduced vertical wind shear over the northern central India, which favors which is either related to enhanced convective activity, or it favors low pressure systems and moisture convergence. So that's likely to increase frequent precipitation events in active spells. Increased vertically integrated moisture transport from the Arabian Sea and the Bay of Bengal, as we just saw. On the other hand, you have increased during the break period. You have on the other hand, you have increased divergence over central India, reduced relative humidity that we saw, increased mean sea level pressure over central India, leading to an anticyclonic circulation, which leads to decreased precipitation events in active spells. Okay, so these are kind of contradictory processes with negative feedback and positive feedback, leading to the net increase of precipitation events in the active spells, but with decreased total precipitation during active spells. Reduced mean sea level pressure over central India, having cyclonic circulation. So that's increasing the intensity of rainfall in break periods. Increased moisture convergence and moisture transport from the Bay of Bengal. So that also increases precipitation event during break periods. Enhanced low-level relative humidity, again favors the same. Enhanced stability is going to drive a decreased precipitation during break period, which is expected. So increased precipitation events in the active spells are then basically leading to decreased precipitation due to decreased CP convective precipitation and low pressure systems. Okay, so let me make sure that LSP is, I don't want to screw that up. Sorry, so that is large scale precipitation as opposed to convective precipitation, which tend to be smaller in scale. I just blanked out on that, sorry about that. So decreased precipitation due to decreased convective precipitation and large scale precipitation. I have a podcast on large scale extreme events in the same series that you can look up. So this is basically increasing mean July-August rainfall. So this is negative feedback to the increase, and this is positive feedback. So increased precipitation due to enhanced convective precipitation and large-scale precipitation during break periods is providing a tendency to increase July-August rainfall, but this is dominated by the decreased precipitation from the active periods, resulting in a net decrease in mean rainfall over the last several decades, but in this case during 2000 to 2019 compared to 1980 to 1999. So obviously again contradicts the idea that maybe monsoon is recovering, but you also have to remember that the latter period, both periods have two big El Niños, the 97-98 during the earlier period, 2015-16 during the latter period, but the latter period also has many more droughts than the former period. So if there are any new results coming along in this direction, I'll add at some point, but this is something I just wanted to highlight as the paper just came out. Okay.